Hello and welcome back to the Embedded System on ARM Cortex Info series. I'm sure so far you're learning a lot and you're revising every session and you're getting yourselves familiar with all the registers, the different buses and different different peripherals that you've been reading through in the reference manual and datasheet. And please go through, if you haven't, please go back and revise again and watch the videos and get yourselves familiar. And today is day 10. Today we're going to learn about exception model on ARM Cortex MX processor. And these are all the sections you're going to learn about today. First we'll start with what is an exception and where it is used, and the types of exception, then the exceptions and the interrupts, what are all the exceptions and interrupts in STM32, and the exception states, and what are all the exception handlers when there is an exception comes from the function call, what happens to it. And then what is a NVIC, nested vector interrupt controller. And we're going to learn about the NVIC registers, where they are used. And then we're going to learn about the steps to program the microcontroller interrupt unit. And then there is an exercise to show all this in a demo, and then we're going to learn about the different priority levels and the different types of the priorities. And then we'll end up learning with the exception. There is two sequences, the entry sequence and the exit sequence. So we're going to learn all of this in today's section. Before moving into the session, I'd like to give a small about us. I'm representing A2DG. It's a startup company started by Anbukars brothers, my brother Alex and Arul, myself, in 2023. Both of us has acquired over 20 years of industrial experience, and we would really would like to share our experience and our knowledge to you all out there, so you can also build your professional growth and end up being a very good professional engineer. And our mission is to convey to at least 100,000 future professionals through our online courses. The main advantage is you could study this course at anywhere, on your own pace at any time, wherever you are. So that's a very good thing. And about me, I am Arul Prakash Anbukarsu. You can call me as Arul, as or APA, as popularly as. I have 20 plus years of experience working in Australia, majoring in renewable energy sectors, in solar and wind, power systems, lead acid batteries, the network embedded systems that contains ATMs, TCRs and POS, banking automation systems and smart parking operations. And these are the expertise I'm majoring in: embedded systems, VLSI and project management. I have a small announcement to make. I categorized into two different categories, the YouTube viewers and internship professionals. All the video sessions that I'm teaching you will be uploaded to my A2DG YouTube channel, so please go in there and review and watch it. To be eligible to get a e-certificate, you have to attend at least 28 classes. That means you have to see at least 28 sessions. At the end of every video, there will be an attendance link, and you have to fill in all your details, and that will be eligible for a e-certificate. As a protocol followed by YouTube, we can't keep more than 2 or 3 days of the videos. It can't live there forever, so they will be erased. So if you want to go back to do your revision, you can't. So that's why you have to go every day and learn every day. So that's why I strongly recommend you and advise you to join our internship programs. And what would that internship program gets you to do? It gets you to acquire an internship certificate, and that's worth a lot. I mentioned this already and I say that again. When you compare with other interviewers, when you're going to that interview or after you land on the first job working with the engineers, your 30 days of this learning experience worth a lot, and you sit on top of everything of the hopes and their expectations, because in the industry they don't have to go through the first few days to train you to get to that speed. You can go on day one and you can start. All they have to give you some instructions and you would be able to follow. Not only that, through our learning management system portal, you can log in. You will have a separate login, and you can go through your video sessions. And once you complete and continue, that will cover for your attendance, and that attendance will fetch you in the end to get a internship certificate. And also you get unlimited access to course contents and unlimited access to course videos. You can pause the video, you can come back and rewatch it again, or you can fast forward and rewind likewise. So there is no limit to it. And if you get stuck somewhere, please contact our backend support team, and they are a very friendly team. They will get to you as soon as they can, and they will help you to proceed along in the course. And these are all the materials required. So please contact Pantex Solutions. The more you practice by yourself and the more you spend time on the hardware, the more information you get, and that's worth a lot. So please do invest on this and contact Pantex Solutions. They would be able to acquire all of these materials. And these are all the documents that will assist you to learn about the concepts today. You need STM32F411, you need STM32F411 reference manual, you need the Cortex reference manual, and you got the AAPCS standard procedure call standard for the ARM architecture that you learned what it is in the previous session. It is a standard set by the processors, that in actual real world, in a major project, in complex projects, there will be big team trying to develop their own subroutines. So therefore they will develop their own stacks in their subroutine, and to develop and to integrate all of that, the processor manufacturers come up with the standard. So you need to follow this standard, so you can unite everything together, so integrate everything together. So that's what a PCS standard is for, and please go through that if you write any new piece of code. I hope you are as interested as I am, so let's connect in and see what this exception is today and what is going to stop us not to learn. Why not? So let's get in and learn. Exception, what is it? In general, anything that disturbs the normal operation of the program. So if your system sends you some error messages, that's an exception. Or how that happens is when the exception comes through, it changes the operational mode of the processor. So that's what in real definition is. Anything that disturbs the normal operation of the program by changing the operational mode of the processor is called an exception. What are all types of exception? There are two types of exceptions. There is a system exception and interrupts. Those that are generated by the processor itself internally, it's called system exceptions. For example, if you hear about the word hard fault or mem fault or bus fault, that's all generated from the processor itself. Meaning if something problem goes on the processor core, on the main processor core, then that relates to hard fault. And if there is any problems in the internal flash or internal RAM, you will come as error as a mem fault. And if there is any problems with the bus interfaces when you try to communicate with other peripherals, and that will come as the exception, system exception. Whereas interrupts are the one created from outside the processor. From the outside, it can come from the peripherals, it can come from other form of sources, except outside the processor. That's called an interrupt. So whenever the processor core meets with an exception, it changes the operation mode to handler mode. As you learned from previous session, whenever there is a normal program runs, that runs in a thread mode. So when an exception happens, what happens? It changes from thread mode to exception mode. So that's what exception is. What are all the exception and interrupts out there in STM32? So recap, when the processor core meets with an exception, it changes the current mode, that is the thread mode, goes to handler mode, and that's where the exceptions are handled. There are 15 system exceptions in STM32 that will be supported to 240 interrupts that supports this M4 processor. So in a total of 240 plus 15, so it can service up to 255 exceptions in this Cortex M4, and that is really a lot in the programming stages. And exceptions and interrupts play a major role in the development process. So if you know all the concepts from through the series, then you will be better off writing and explaining to other engineers what this all about, and also itself grow yourself by learning all of this. The types of exceptions and interrupts, it's in Cortex M4 user guide on page 34. I'll show you where it is. So opening the Cortex M4 devices, so going to page 34. This is the exception model I'm going to learn. So there are few exception types as we learned from the slides. We got 15 exceptions. The first exception, every exception comes with a priority level. So the top priority level is always a reset, and then the NMI, non-maskable interrupt, and then the hard fault. So what is a reset? The reset is invoked on power up or a warm reset. When you start the when the power comes through and the processor restarts, and that's a power up reset. And what is a warm reset? When you press the reset button on the processor, on the nuclear board, and it starts the reset process, and that pressing that reset button is called a warm reset. And the execution restarts as privileged execution in thread mode. In NMI is a non-maskable interrupt. It's generally signaled by the peripheral. So some peripheral from there, it gets the priority and sends to the exception. Excuse me. Sorry. The hard fault is an exception that occurs because of an error during processing. Sorry, excuse me. Sorry. Exception while processing happens in the processor core, and that's where you get the hard fault. If there is any mechanical fault or mechanism that's not budging with what the exception wants to do, and that's where you get the hard fault. The mem-manage is a fault exception that occurs because of a memory protection related fault. If the memory protection goes through any problems, then you get the mem-manage. And the bus fault is an exception that occurs because of a memory related fault, whether it can be an instruction fetch or a data memory transaction. And the usage fault can be occurred by any undefined instructions or invalid state or instruction execution, or error in the exception return, which you will learn from the entry in the exit sequence, and that's the exception return. So through that you will get the usage fault. And then there is the supervisor call, is an exception that's triggered by the SVC instruction. In the last session we learned about SVC handler. So we created an exception handler, and we asked the function call to go to that SVC and do that function and then return back. So something, if that goes wrong, then you'll get ISV call. And pend SV is an interrupt driven request for system level service. In an operating system environment, use pend SV for context switching when no other exceptions is active. So you're going to use the pend SV to prioritize yourself, and you're going to switch between one to the other, active and non-active. And then there is a system tick. That's an exception the system timer generates when it reaches 0. When all the exception goes through and everything goes by the priority, when it hits 0, then the system tick will come. There is no more priorities or no more exceptions. What do you want me to do? So it gives us a system tick message. And then the IRQ, an interrupt or IRQ is an exception signaled by any peripheral or general by a software request. And this is the different exception level, and they always go by the priority. The lesser the value, the highest the priority. So -3 is the less value, so reset comes first, and then the -2 of NMI, then hard false. So likewise, and there are some reserved numbers for internal interrupts. So these are all the exception handlers. So let's go back to our learning today. So these are all the things that we covered: NMI, hard fault, mem manage, bus fault, usage fault, SV call, pend SV, system tick, and IRQ. Then now let's talk about the exception states. As you can see from the slide, it is on page 34 on Cortex M4 user guide. On 34, you got 4 different states. What are they? They are inactive, pending, active, and active pending. What is an inactive state? If the exception is not active and it's on pending, so that means it's working on a different exception, then it's called inactive. But it's still in the list, it's still in the queue, but it's not, the processor is not working on that particular exception. That's set to be in the inactive state. The pending state is the exception is waiting to be serviced by the processor. So next down the list in the queue, so that will be in the pending. An interrupt request from a peripheral or from a software change the state of the corresponding interrupt. That will put to the pending stage. And active is the one that currently the processor works on the exception. That's called the active one. And active and pending is the exception is being serviced by the processor, but still there is something pending that comes through from the same source, and that's will act as the active and pending state. So these are all the 4 different active and pending states. Let's go back to our learning. And next one is the exception handlers. What is exception handler? So when you get an exception, the program halts the current mode, which is the thread mode, and immediately it goes to the handler mode and it handles all the exceptions. So that's what exception handler is. And being it's going to link with the interrupt, it forms a routine. So you call it as the processor manufacturer call it as an interrupt service routine. The IRQ interrupts are the exceptions handled by the ISRs, interrupt service routines. And there is 2 different handlers. There is a fault handler and a system handler. Fault handlers are nothing but what the system generated from the processor generated. So the hard fault, mem manage, usage fault, the bus fault are by the internal processor, whereas the NMI, pen CV, SV call, and system tick are caused by the system handlers, can be handled by the system. Now we've been talking about earlier in the last sessions vector table. What is it? What is a vector table? A vector table is nothing but it's an array of addresses. It will have plenty of addresses, and every exception will have an array starting address, so that's what it's called a vector table. A vector table also contains the reset value of that stack pointer, and the start addresses are also called as exception vectors for all exception handlers. So let's go into reference manual, page 198. You will see the exception handler. So I'm going to the reference manual and page 98. Sorry, what did I say? 198, sorry. Page 198 on the exception handler. You will see the vector table, the interrupts and the events, and this is the vector table. So every exception and interrupt will have its priority and its position, and also it will have its addresses. For all that exception, you will have a start address where that is actually, and also it will have a priority. So this is a vector table. The reset address is 0000 and 0004 and has a priority of -3. Likewise, the NMI will have this address, when the type of priority it says fixed, it means it can't be changed. It's not flexible. But when you see a settable, that means you can manually interrupt that, set that interrupt, set that exception. So likewise, there is for everything you got the addresses, for DMI, for timers, for I2C, that's the vector address, the SPI, the USARTs. The USART2 is the one we're going to learn later on. It's the IRQ number is 38. So likewise, so this is the vector interrupt table on page 198 on your reference manual. So this is what you would see on page 198. So there you go. You see all this fixed and the priorities and what each and every address shows. So that's the vector table. You get it from the vector table. Next, let's go to learn about processor core. So to do that, just one sec. Processor core. Okay. So let's see what's the ARM Cortex M3 or M4 processor core peripherals looks like. So as we know from M4 architecture from day or session 4, these are all the peripherals that it has: the CPU core, the nested vector interrupt controller, the floating point unit, the memory protection unit, the SCV, the SysTick timer, and the debug. These are all the peripherals it's the ARM Cortex M4 has. And as we learned earlier, this is the system exception control registers. In the previous session, if you want to get to flash memory and the SRAM memory, you can do so by the code regions via the data bus and the instruction bus, and they are all 32-bit as you learned. But if you want to connect to SRAM peripheral or external RAM, then you need to use a system bus. And if you want to go to private peripheral bus, then you need to interface with that PPB to get into the vendor specific regions, and they are all these are all Cortex M4 processor bus, and this is a vendor specific bus. So recap of the bus access: every code instruction fetches are performed over the instruction bus, and the SRAM fetches data are performed by the system bus. The SRAM bit band works with the alias region, and the peripheral fetches both the instructions and data, and they are performed by the system bus. Peripheral bitband memory map also works on the alias region, and it has instruction accesses. The external RAM fetches instructions and data over the system bus, so as the external device. The private peripheral bus will hold external and internal interface region. This memory region is execute never extend, and so instruction fetches are prohibited, meaning you can't use it, and MPU if present cannot change this. And there is a system as an MPU from the system peripherals. System control block. So let's talk about the private peripheral bus. The private peripheral bus interface provides access to internal and external processor resources. What are the internal private peripheral bus can be interfaced with? Being internal, it can be interfaced with the ITM, the instrumentation trace macro cell, and also it can be interfaced with the data watch point and trace DWT, flash patch and breakpoint, and also with the memory protection unit and the nested vector controller, interrupt controller. Whereas if you use the external processor, then you got to access to trace point interface unit, the embedded trace macro cell, and the ROM table, and the implementation of the PPB memory map. The system control block registers, SCB, or the system control block registers, provide system implementation information and system control. This includes the configuration of each and every types and the control and the reporting of the system exceptions. You can see this on the generic M4 devices generic guide on page 227. Just one sec, I'll open that and show you the generic page. Let's see, generic, sorry, what's the page number? 227 in generic. 227. So this is the system control block where you got the different registers of system control register. There is a configuration and control register. There is a system handler priority register 1, system handler priority register 2, system handler priority register 3, system handler and control. So these are all some of the system control block register. Through this you can configure and you can control and report to the system exceptions what the system control blocks are doing. Okay. So this is what we just saw. The system control block provides system implementation information such as configuration, can control and report system exceptions. Through the system control block registers, you can enable fault handlers. You can get pending status of the fault exceptions. You can also control its sleep and wake up settings. You can also configure the priority of system exceptions and the system tick timer control and its status and unaligned data access items. Again, you can go to page 227 and you can read through, and everything is there to explain about the system control block SCB registers. By default, with the exception status, these are all the various exceptions that's listed as a default. If it is a hard fault exception, it's always enabled by the default, can be masked. NMI, it's always enabled by the default and cannot be masked. The usage fault is disabled by default. The memmanage bus fault systic exception triggers whenever there is system trigger is enabled and expires. So therefore, if there is 0, it will go as system tick and it will enable that. And the SVC exception triggers only when the SVC is introduced. And pend SV and debug monitor, it's disabled by default. So these are all some of the default settings that comes with your STM32. Now let's get to learn about nested vector interrupt controller, NVIC. NVIC is part of the processor core. It sits inside the processor core and directly interfaces with the Cortex M4. The nested name comes because if the program handling the current priority level, if there is another priority or another exception hits to it and it comes from the same source, then it doesn't know which one to go, so it preempts to that priority. So the nested is it combines to that and then it goes to the new interrupt or new event that asks it to do, and that's what the term nested is. So it classifies as high priority and the lower priority. And these are all set from the ARM Cortex M4 processor cores, so the NVIC directly interfaces with that. As you can see, NVIC is one of the peripheral of the Cortex M processor core. It is used to configure 240 interrupts. Using these registers, you can enable or disable, or you can do pending interrupts and read the status of whether it's an active or a pending interrupt. So this will determine whether that interrupt is an active one or a pending one, and also you can configure the priority and priority group of various interrupts. It is called nested because it supports the preempting of a lower priority interrupt handler to the higher priority when it arrives. So if the program works on the lower priority and when a higher priority arrives, it stops the low priority and goes into handling the higher priority and then comes back to the lower priority. So that's accumulation or accommodation of handlers is termed as nested. As we know, Cortex M4 supports 240 interrupts. The STM32F11 used and referred in the manual page on 248. The something that the handler comes through an exception by a peripheral, not by the processor core, then that's something like a SPY or I2C or USART. If that sends through an exception handler to the program, and that's caused by the third-party vendors, whereas NVIC comes from the ARM core processor itself, so they have their own exception handles. The STM32 has 82 maskable interrupt channels and up to 86 maskable interrupt channels on S242X and 43X. And this STM32F11 that we are learning has 16 programmable priority levels. That's 4 bits of interrupt priority, and it has a low latency, that means it's high speed, and power management control, implementation of system register. So for example, in the vector table, if you see the priority as settable, that means you can change or alter its value by manually setting to that value. And this is how you deliver to the processor from the external, from the peripheral side versus processor side. As I said earlier, process side, the ARM Cortex M4 core, M4, directly interfaces to the NVIC. And from the peripheral side, from the external, if there is anything comes from the external interrupts, it will use the EXTI, and this is how the GPIOs and the USART or GPIO or I2C or SPI, if they have any interrupts coming through, this is how they get fed to the NVIC, which sits inside the processor core, and it directly communicates to the processor core, and the core will understand, okay, that's a priority, so I will handle that first. So this is how it's set up from the peripheral side to the processor side. This is just one example with the microcontroller with the processor core. Actually, we're going to learn about USART2 and its IRQ is 38. This is another microcontroller where, as an example, I pointed here, USART3, that IRQ is 39. The NVIC registers. If you go back to the M4 reference manual on page 219, you will see the different NVIC registers. They are nothing but the interrupt set enable registers. Interrupt, after you set the enable, you can clear that enable register through this. That's the ICER. Only 2 registers are we going to use in the exception handler. So ICER and ISPR, which is the interrupt clear enable register and the interrupt set pending register. And what you set as a pending register, you can also clear by this ICPR 0 to 7. And there is the interrupt active bit registers, and there is the interrupt priority registers, and there are software trigger registers. So if you take NVIC registers, referring to the reference manual on page 20, you got to start with learning about interrupt set enable register. So this is the register that will set you to help you to set the interrupt, and it has 32 bits 0 to 31. So in this example, we're going to learn about USART setting. In the real world, all that exception handler done by the processor itself, but here, just to give you an example, we're going to create the exception handler as a manual entry. So I'm going to show that to you through this ISER register. And USART is IRQ as 38. So if you remember, if you go to the vector table on the Cortex vector table, if I think it's page 198. No, sorry. Page 34, I think. Yeah, exception states. Scroll down, that's the exception priorities. Okay, I showed you earlier the exception vector table is, hang on, I'll just type vector table here and go there directly. Vector table. system control blocks. So that's a vector table offset, and let's see vector table that I referred to you, exception model, exception types, vector table. So we are talking about usert. So usert will live after this. Exception priorities, vector table. Vector table, okay. So the ISER0 comes in handy, and our USAR2 is value is 38, so we got to use ISER1 because this counts from 0 to 31 and the next register starts from 32, so you need to enable that. And also you got to use interrupt clear enable register. This is the register where you use to clear the bit where you set as an enable and wait for the active and the pending state to start. And then you have to use the interrupt set pending registers. This is where you're going to amend into your exception queue. You're going to set that register as well. And there is clear pending registers. There is active bit registers. And this is the exercise that I'm going to show you to enable and do the pending of USAR2. USAR2 IRQ is 38, and that outside peripheral comes from outside, going to communicate or interface with NVIC. The NVIC is going to connect to the processor core. So these are all the steps to program MCU program. The first point is you need to identify where the interrupt request is from the vector table. You need to go to the vector table and identify, for example, with this USAR2 we are going to learn, and that's IRQ is 38. So once you find the number, then program the processor register to enable. You have to enable that register first and then set its priority level if you want to, but it's just an optional. Then configure the peripheral using its peripheral configuration register when a packet is received. When the interrupt is issued on the IRQ level, it gets pended in the pending register of the processor. So this time the NVIC will allow the IRQ handler plus the IRQ number to run into its priority, and that's how the interrupt works with the priority level, as you can see from these steps. As you can see from these steps. Please note that if a peripheral issue and interrupt and IRQ is disabled, then the interrupt will get pended into the pending register of NVIC as soon as the IRQ is enabled. So this is the process of peripheral interrupt exercise that I'm going to show you. Pick courtesy to Pantech Prolabs. It's so attractive. I keep going back to them and accessing their pictures, and they were so honorable to let me to use their pictures. So thank you to Pantech Prolabs as well. So this is how the pending register gets amended to NVIC. First, the data arrives from the external peripherals. It gets sent to stored in the user receiver buffer. This is where the peripheral issues and interrupts saying there is something coming up, and I'm going to amend that to the NVIC. Then that issue is sent to the PR register, the pending register, where a register value is formed, and this PR value with the IRQ enable set goes combined to the NVIC. The NVIC then fetches the ISR address, the interrupt service routine address, from the vector table, and the program counter now jumps to the ISR. So once the program counter done its job, then the interrupt service routine copies the data from the RX buffer and sends to the SRAM memory location. So this is how a peripheral interrupt exercise works. And these are all the programming steps. Identify the interrupt request number of the peripheral by referring to the vector tables. Then how are you going to do? This is the one I'm going to show you in the program now. First, choose the ISPR register based on the IRQ number, the interrupt number, and set the pending register IRQ modulus 32 we our IRQ number is 38, and if you do modulus of 32, you need to enable that bit. So that's what this pending register actually does. Choose IRQ handler function from startup file, and you will go. So I will open the IDE for you, and I will start creating a project, and I will explain this in a program. So I'll stop this, it will shut down and go back to normal. So I'll create a new project. So file, new, STM project. Okay, if you'd like to go for a break, please go and have a little break, and when you come back, I'll show you how this program that I'm going to show you will. I'll see you back shortly in a couple of minutes.